All right, so we've established then that there's some experimental evidence that definitely backs up this idea that matter has wave-like properties. But it's still not altogether clear when would you want to call it a particle, when would you want to call it a wave. And are those two formulations mutually exclusive, or are these just aspects of what matter can do under certain conditions? Well, let's take a look at some of the problems that we run into if we think of matter as having just regular particle-like properties and not being a wave. Okay, so there are some serious problems with this. First of all, in the atom, it's found that if you use the principles of electromagnetic waves for particles, the electrons in the ground state of, for example, hydrogen or any other atom, should radiate energy and fall into the nucleus. And so in other words, here we've got, we'll look at the simplest of all atoms, the hydrogen atom, which has one proton, one electron circling around it. By the time that the electron gets into what we call the ground state here, which is the lowest state energy that an electron can occupy in an atom, according to the principles of electricity and magnetism that were developed in Physics 2.8b, were done by Maxwell, we have an accelerating electron. And as it accelerates, it's changing its direction as it goes round and around the nucleus. Because it's accelerating, it should radiate electromagnetic waves by Maxwell's equations. So those electromagnetic waves should be given off in all directions, but because that is lowering the energy of the electron's orbit, because that energy has to come from somewhere, has to come from the electron should spiral in toward the nucleus and crash into the nucleus. Okay, so this is the prediction then of classical physics without quantum mechanics. And the wave-like properties of particles. But what is observed is that the electrons are stable in the ground state. In other words, they don't spiral in. And they give off no energy in the ground state. So we might wonder then, well, it seems like what we've discovered here is a flaw in the predictions of classical physics as it relates to the properties of matter. And this is just one problem. There's more than one. Another problem that we have is that the electrons should be able to be in any orbit around the nucleus. And as the electrons change from one orbital level to another, they should give off a continuous spectrum of energy. This is what we expect from classical physics. So again, we could connect that in with this statement here. This is the prediction without quantum mechanics and without the wave-like properties of particles. But what is observed in this case is a discrete line spectrum. Excuse me. Indicating that the electrons can only give off certain energies. Okay, and so let's just take a quick look at what's observed then for different kinds of atoms. Down below is a continuous spectrum with the hydrogen lines taken out from the sun. But what I'm trying to show here is not an absorption spectrum, but rather just that continuum of colors going from red to blue. So that's what you would expect an atom to give off if the electron could be in any orbit. Then it could go to any other orbit and it would give off every single possible energy. But if it can only jump from one to another, then you would expect a line spectrum. So the idea then with a line spectrum is that the particles can't just exist any old place, but can only exist in certain orbits. So this might be n equals 1, this might be n equals 2, this might be n equals 3, this might be n equals 4. But if the electron were anywhere in between, it couldn't even exist. But it has to be either here, then it would give off one energy. That energy would be the difference in energy between these two states as a photon. Or it could be given off in this energy here. Or it could be given off in this energy and then in that energy. So that would give off another photon plus another one that looked just like this one. Or it could be in this state. It could give off this line, and that line, or this line and that line, or this line and that line. And so you get a bunch of different possibilities, but it's a finite number of these discrete amounts of energy in the form of photons. Okay? And so what the observation then indicates is that the electrons can only give off certain energies, and therefore they must only have certain orbits. Now how can we, now the particle model is not helping us one bit here, but what if we went to a wave model? Then what might we come up with? Well, you could imagine, if we look up at the data projector, that we could have a constructive interference between similar waves that move in opposite directions. So for example, you could imagine then an electron wave as being kind of like a vibration, let's say, on the surface of a glass, in which the glass starts to resonate, vibrates more and more, until finally the glass breaks. Or you could imagine a ringing bell. Okay, in a ringing bell, you get different modes of oscillation that are possible that correspond to constructive interference under certain conditions. And so that gives you the tonal qualities of that bell. Or you could have an earthquake on the surface of the Earth. That earthquake could send off waves in opposite directions, and certain waves that have a particular value for their wavelength could send the Earth ringing, just like a bell, in different modes of vibration. And that would be a standing wave pattern. Now, I've already shown that electrons can have a wavelength. So couldn't we have something like that with the electron? What if the electron, instead of being a particle, is a standing wave pattern in which, remember with standing waves, you need to have similar waves constructively interfering that are moving around in opposite directions. So this would be the same electron that would be constructively interfering with itself as it travels round and round in opposite directions. So in other words, we think of the electron wave as being a standing wave pattern. And since the electron only has a certain finite wavelength, there would be a certain minimum size that this standing wave pattern could take up. In just the same way as if, say, you had a vibrating string, there's only a certain length of that string that could allow for a standing wave pattern to be established. If you went any closer in than here, if you put B here, and you go in any closer than that, then you're going to get destructive interference and the wave will cancel out. So similarly then with the electron wave, there must be a certain minimum radius at which the electron can exist. And that would be the n=1 standing wave pattern. Okay, and so the condition then on this would be that 2 pi r, where r would be the radius of the electron's orbit, has to equal n lambda. Has to be a whole number of wavelengths. And so that would be your standing wave boundary condition. Okay, so this is just like the standing waves that we looked at before. Remember, they're constructive interference of similar waves moving in opposite directions. But for the most part, we were making the reflection happen off of a closed or an open end of a tube. We didn't have the system wrapping around on itself. But if you do, then you just have to have a whole number of wavelengths equal the circumference of this circle. And then you can get the wave going back into phase with itself as it travels round and round in opposite directions to produce the standing wave pattern. So how does this help us with what's being observed here? Well, the electrons only give off certain energies when they go from one standing wave pattern to the next. So that'd be like going from one harmonic tone to the next in a vibrating string by adding energy to the system. Okay? And also here, we can see that if you're in the ground state, you can't be any lower than the ground state because then the electron wave would cancel itself out by destructive interference. So this allows then for the electrons to only be at certain distances away from the nucleus that satisfy our standing wave boundary condition. And so Niels Bohr took this and started running with it, said, okay, well this seems like we're on the right track then to think of the electron as being a standing wave. Now, again though, when do we think of it as being a particle? When do we think about it as being a wave? That's a big question. And it depends on what kind of information you're trying to get out of the system, really, whether you want to consider it to be a particle or a wave. But for this kind of a problem, it's better in this situation to think about it as being a wave. Okay, so that's one thing. Another thing is that it also has to satisfy the principles of physics. And so here we've got a positive charge and a negative charge. There's going to be an attractive force. That attractive force, the electric force, is going to equal 1 over 4 pi epsilon naught times E squared over R, where E, the magnitude of E is the charge on an electron and a proton. So the E value is just our good old friend, 1.6 times 10 to the minus 19 coulombs. And that's going to be an attractive force, so that's going to be our electric force, but that's also our centripetal force, isn't it? Because that's making, at least with what we call an S orbit, something that has spherical symmetry to it, we can say that this has to equal mv squared over r, which is our centripetal force, okay? Because we are requiring that this thing go round and round in a circle. Okay, so Niels Bohr then decided that the electron also not only has wave-like properties, but now, in a sense, we're kind of schizophrenically jumping back and forth. And we're saying, well, but it acts like a particle too, you see? Because if it's a particle, then it's going to satisfy this centripetal force relationship equals the electric force. And there's one other principle that this electron has to satisfy. That's the principle of conservation of energy. You can say that 1/2 mv squared plus our potential energy, which in this case is going to be minus E squared divided by 4 pi epsilon naught r, has to equal our total energy. Okay. And so if we take these three equations, do some manipulations to them, and you'll see this in chapter 39 for the details. What we find is that the energy, En, is equal to minus 13.6 eV over n squared, where n is an integer value, can equal 1, 2, 3, any positive integer that satisfies our standing wave boundary condition. So n equals 1 then would be the ground state. So E1 equal minus 13.6 eV for hydrogen. This is for hydrogen. We're looking at the simplest of all elements here. So E1 is minus 13.6. E2 would be equal to minus 13.6 eV over 2 squared, which is 4. E3 would be minus 13.6 eV over 9, or 3 squared, etc. Okay, so this result then just comes by solving equations 1, 2, and 3 simultaneously. Just putting all of that information together, we get this expression for the energies. So sure enough, that's the kind of thing we're looking for over here. We're looking for a difference in energy that can have associated with it a photon wavelength, because the difference in energy will be manifested by a photon being given off by the electron. So you can think of the electron as jiggling a little on its way from one of these energy states to another, and then producing the photon, which is equal in magnitude to the difference between those two. Okay, so that's one of the important equations. And the second one is Rn is equal to n squared times A naught, where A naught is what we call a Bohr radius. So this is the minimum radius of the electron in the hydrogen atom. And that's equal to 0.51 angstroms. Okay, just by combining together the different physical constants. Here, this would be the mass of the electron. Epsilon naught is given, and the charge on an electron and a proton are all given. And so this ends up being our minimum Bohr radius. So we can see then that what this does is this describes then for us a system of allowed orbital states for the electron around the hydrogen atom that are separated by distances of A naught, or 0.51 angstroms. Then the next one out, that would get constructive interference and be a standing wave pattern, would be at 4A naught. Then the next one would be at 9A naught, etc. Okay, and so whether or not this all works out or not is dependent on whether we can get a difference in energy here that corresponds to one of our observable photons. So we go back here to hydrogen and we see, okay, well there's a few observed lines here for hydrogen. And so if we can plug in the difference in energy into that equation and solve for a wavelength, then maybe we could find all of these wavelengths, if that theory is right. And so using the Bohr model then, we can check it and see whether or not it's giving us the right values for the energies of the photons. So let's check the Bohr model then for a visible photon. So this would be a transition then to n equals 2, it turns out. And not n equals 1. So in other words, to get visible photons, it's called the Balmer series, we need a transition from n equals 4 to n equals 2, or from n equals 3 to n equals 2. Let's try the lowest possible energy transition. Delta E here is going to be equal to E 3 minus E2. Okay, so we're in the third excited state. We're going to go to the second excited state. Okay, and so associated with that, we'd have a change in energy, a difference in energy, that would be equal to minus 13.6 EV over 9 minus a negative 13.6 EV over 4. Okay, and so that would give us 13.6 times 1/4 minus 1/9. So that gives us 1.89 eV. Okay, so that's our difference in energy then. That corresponds to essentially the lowest possible energy that has a transition to the n=2 state. And so let's convert that to joules. So that's going to be 1.6 times 10 to the minus 19 joules per eV. So that'll give us 3.02 times 10 to the minus 19 joules. So let's set that delta E equal to hc over lambda, because this difference in energy must turn into the energy of a photon. Or the photon's wavelength, which we can get right off of the screen there by experiment, is going to be equal to hc over delta E. So that'll be 6 and this is lambda 32 here. So that's going to be the wavelength of the photon going from state 3 to state 2. 6.63 times 10 to the minus 34 joule seconds times C, 3 times 10 to the 8 meters per second, divided by, we have to have this in joules, which we did, 3.02 times 10 to the minus 19 joules. So hopefully, let's keep our fingers crossed that this is going to give us one of the observed photons in the bright line spectrum of hydrogen. Okay, so that gives us 6.58 times 10 to the minus 7 meters, or that's 658 nanometers for lambda 32. So let's go back and look and see. Well, I don't have a fine grid on this thing, but this kind of orangish looking light here looks like it's a little less than 700, a little more than 600, and it's more than halfway. So it looks like this is it. That's the one. We did it. We found a beam of light, a photon of light that has the right wavelength and the right energy to be satisfied by the Bohr model. And so if we go through and we do that with the rest of these different energy levels, we find that they also, if we have transitions to n=2, will give rise to all of the visible photons that can be seen. Transitions to n equals 1 so in other words, if the ground state is the final state, this gives rise to ultraviolet photons. Whereas transitions to n equals 2 gives us the Balmer series, which are the visible photons that we see. And these are the easiest ones to use to verify because we have eyes that can see with these, whereas we need UV or infrared detectors for other transitions. And so this is often called the Lyman series. That's transitions to n equals 1, the UV photons. And then transitions to n equals 3 is the Patchen series. Those are, as you might guess, infrared photons. So at least for hydrogen, this seems to be working very well and is giving us things that we can measure in the laboratory. But is there another way of looking at this? A way that might help us to understand how this all fits into the concept of our new quantum physics paradigm. Of course, it's not new anymore, but we call it modern physics because this stuff came up starting around 1900, and in the 1920s it really started to flourish, and we got things like the Bohr Atom. Let's take another look at this. From the standpoint of the uncertainty principle. Because we're trying to get used to using the uncertainty principle, and it turns out that it can be applied in so many different areas. Okay, so what we've got then with the uncertainty principle is something that looks like delta p delta x is approximately h bar over 2. Okay. Now, if we've got an electron going around a proton, we can first of all say that, well, if the proton's going this way, it's got a momentum p. If it's going this way, it's got a momentum minus p. So our uncertainty in the momentum, delta p, give or take a factor of 2, should be somewhere around the same value as the momentum itself. Because we're going here from plus p to minus p, or we have an average momentum of 0, which fluctuates between plus p and minus p. Okay, so we can say that. And we can also say that this is equal to h over lambda, where lambda is the wavelength of the electron. And we can also say that delta x is approximately equal to r, because the uncertainty in the position has to go between plus r and minus r. Or in spherical coordinates, that's just r. Okay. And so think of this as being, think of this as being our uncertainty and momentum. And we can think of this in this context in terms of the delta x being related to r. That's what I meant to do there. Okay, because the delta x in this expression is approximately equal to r. So delta p is approximately equal to p. That's equal to h over h bar, essentially over 2 delta r. Okay, like that. Okay. And so once we've established that, we can write an expression for the total energy. Now, in our total energy expression, we can say that the total energy, if it's non-relativistic, is the kinetic plus the potential, or 1/2 mv squared minus E squared over 4 pi epsilon naught r. But what I'd like to start doing from now on is writing for the kinetic energy, instead of 1/2 mv squared, we'll write that as 1/2 times m squared v squared over m. Or we can write this as p squared over 2m. So from now on, instead of writing kinetic energy as 1/2 mv squared, because the momentum is such a basic quantity in quantum physics, I'm going to start writing it as p squared over 2m. Because that allows us to do a lot more with connections that we have between the uncertainty principle and our fundamental relationships of momentum and displacement. Okay, so if I have P then is equal to approximately, by the uncertainty principle, h bar over 2r, then I can rewrite this then as h bar over 2r squared over 2m minus E squared divided by 4 pi epsilon naught r. Or we can rewrite this as h bar squared divided by, here's a 2, squared is 4 times 2 is 8. It's 8 mr squared, and this should be capital R here, minus E squared over 4 pi epsilon naught r. So this is an expression for the total energy that is consistent with the relationship between P and delta P, x and delta x, okay, which is in this case r. Okay. And so what we can do with this then is differentiate both sides of this equation with respect to r. If we do dE dr, essentially what we have is something that has a certain energy state to it, E versus r. And if we take the derivative of this at a point when the slope is 0, what we find is the minimum energy. This would be E minimum. This would be the value of r that corresponds to E minimum. And then this value here would be E minimum. Now it could be a maximum too, but it turns out that in this kind of a situation, we end up with a minimum energy, and you could do a second derivative test to show that that's true. But if we take dE dr, set that equal to 0, what we find is that r is equal to 4 pi epsilon naught h bar squared divided by m E squared. And that, as it turns out, by the algebra that Bohr used in his Bohr hypothesis, is A naught. Okay, so by using the uncertainty principle, combining that with the principle of conservation of energy, and then finding the minimum energy of a particle, what we find is that minimum energy is at the Bohr radius. So this R at E min then is just A naught. And so what does that tell us? Well, it tells us that this is the most stable place. And so why would it want to radiate energy if it's already at its lowest state of energy? Okay, and so by looking at this from a wave properties, we can say that by having a minimum energy at the Bohr radius, it's not going to want to radiate energy if it's at any other value other than the Bohr radius. And so then that shows that the idea of our standing wave particle only existing down to the Bohr radius but nowhere closer to the nucleus than that is consistent with the uncertainty principle combined together with the principle of conservation of energy. And I welcome you to do the math on this and to work this out. Take dE dr, set that equal to 0, and show that you do in fact get this condition on the Bohr radius. Okay, so what would happen then if it were in closer? Let's say the electron dared to come in closer than the Bohr radius. Well, then the delta x would get smaller than A naught, and that would make the uncertainty and momentum have to go up. Because as one goes up, the other has to go down. So if you're saying that, oh, I'm more certain as to the location of the electron than the Bohr radius, then that automatically, from the uncertainty principle, makes the uncertainty and the momentum higher. But what happens if something has momentum, and the uncertainty momentum is proportional to the momentum itself? That's going to throw it back out. So you try to push it in to obtain a better resolution, it automatically pushes itself back out because it has more momentum, more uncertainty momentum, and therefore more momentum to overcome that increased resolution in the position. This, again, is all coming from the fact that you can't simultaneously know the position and the momentum. And the more well-defined one of those quantities is, the less well-defined the other one is. What if it goes out farther? What if it goes out here? Well, now your uncertainty in the position has gone down, or has gone up, I should say. So if this goes up, then your uncertainty in the momentum is going to go down. But since your uncertainty in the momentum is proportional to the momentum itself, then that means that it's going to slow down. But if it slows down, that's going to drop it back down into the ground state. Okay, so either way, if you try to squeeze in on it too tight, it goes faster, pushes itself back out to the Bohr radius. But if you loosen the constraint on where it is, then its momentum goes down and it drops back down to the ground state. So this is a way then of connecting in the ideas of what we already know about physics to the consistency of energy as it relates to the uncertainty principle.